Hello everyone, welcome back to my attempts at learning Rust while recording it. Last time we finished the fourth chapter in the book, and today we'll start the fifth one. And we'll learn about structs in Rust. Great, let's start. A struct or a structure is a custom data type that lets you package together and name multiple related values that make up a meaningful group. If you're familiar with an OP language, a struct is like an object's data attributes. In this chapter, we'll compare and contrast tuples with structs to build on what you already know and demonstrate when structs are a better way to group data. Well, that's kind of the other way around. Classes came after structs. We'll demonstrate how to define and instantiate structs. We'll discuss how to define associated functions, and especially the kind of associated functions called methods. Okay, so it's okay. To specify behavior associated with a struct type. Structs and enums discussed in chapter 6 are the building blocks of creating new types in your program's domain to take full advantage of Rust's compile time type checking. Let's go. Okay. Let's just cargo new chapter 5 and then code into chapter 5. Excellent. Let's open the main, open our terminal. Excellent. Okay. Okay. Structs are similar to tuples discussed in the tuple chapter, in that both hold multiple related values. Like tuples, the pieces of a struct can be different types. Unlike with tuples, in a struct you'll name each piece of data so it's clear what the value mean. Adding these names mean that structs are more flexible than tuples. You don't have to rely on the order of the data to specify or access the values of an instance. Okay. To define a struct, we enter the keyword struct and name of the entire struct. A struct's name should describe its significance of the pieces of data and data being grouped together. Then, inside curly brackets, we define the names and types of each piece of data, which we call fields. For example, listing 5.1 shows a struct that stores information about a user account. So let's look. We have a struct user is active boolean, its username, email, and signing count. Which is a U64. To use a struct, after we've defined it, we create an instance of that struct by specifying concrete values for each of the fields. We create an instance by stating the name of the struct and then add curly brackets containing key value pairs, where the keys are the names of the fields and the values are the data we want to store in those fields. We don't have to specify the fields in the same order in which we declared them in the struct. In other words, the struct definition is like a general template for the type, and instances fill in the template with particular data to create values of the type. For example, we can declare a particular user as shown in listing 5.2. So let's try to do this, and let's play around a little bit. So we have struct user active pool. Is it? Yeah, it's a comma. Username string. Email string. And sign in count as a U64. Okay, and no semicolon at the end. Okay, and now I want to instantiate this and let user1 equals user. Okay, I define it like this. Then I open the curly brackets and have active true. It's not equals, it's also a colon. That's interesting. Username is string from hello user, of course with a capital letter, and email will be string from user at hello.com. And of course I forgot colon here, then semicolon, and sign in count 1, and I close it with a semicolon. Now everything works, just unused. But if I omit something, okay, so there is no partial initialization of structs. Okay, maybe there's something like a default value. No, well, maybe there is, and I don't know yet. So let's bring it back to working order. Okay, let's continue. To get specific value from a struct, we use dot notation. For example, to access the user's email address, we use user1email. Let's check this out. First, I want to see if I can do this. Will this work? No. So I have to do it like this. And it should work. Excellent. Oh, it also warns me that I'm not using these fields. Okay. So, done. Let's see what's the type. It says it's the user is immutable. To get a specific value from a struct, we use dot notation. For example, to access the user's email address, we use user1email. If the instance is immutable, we can change a value by using the dot notation and assigning it into a particular field. Listing 5.3 shows how to change the value in the email field of the mutable user. Okay. Yeah, makes sense. Let's just make sure that this is user1. Oops, sorry. So this type of is user, and this is borrowed, so excellent. And if I want to have a mutable user, I can add user1. Oh, I wrote sing and not sign. Yeah, and I add 1 to this. Great. Okay, let's continue. Now that the entire instance must be mutable, Rust doesn't allow us to mark only certain fields as mutable, as with any expression. So I can't put mutable here. Like if I try like this is an error. Okay. Yeah, it makes sense. Yeah, you don't want to go into partially mutable structs. Yeah. If you want to change a part of a struct and make sure other parts are the same, you should use something like methods or functions to use that. Okay. Note that the entire instance must be mutable. Rust doesn't allow us to mark only certain fields as mutable. As with any expression, we can construct a new instance of that struct as the last expression in the function body to implicitly return a new instance. Listing 5.4 shows a build user function that returns a user instance with a given email and username. The active field gets the value of true, and the sign-in account gets a value of 1. So here, basically, we have a function that build user that gets an email, which is a string, and a username, which is also a string, and returns a user. And basically, we return user with, let me just copy it. And here we have the name and email. So let's just make sure. First, let's do this. This should work. Sorry. This email and username like this. Great. So now this creates the string. Let's just go through the borrow checker. This creates an immutable string. This function borrows this string. Then the username our parameter borrows this string as well, and then creates a new object and then this user1 borrows it back. Makes sense. Okay. And this is the function. Yeah. Okay, and just to make sure that we don't need to preserve order, let's see that it also works. Great. Okay, using the field init shorthand. Okay, so there is default some things. Okay, it's not default. Because the parameter names and the struct field names are exactly the same in listings 5.4, we can use the field init shorthand syntax to rewrite build user so it behaves exactly the same but doesn't have the repetition of username and email as shown in listings 5.5. So I can, if I have this username, I can an email, I can omit it. And because it has the same name, but I cannot do it with a name, right? This will be an error. But if I change it to username, then everything is okay. Okay, here we're creating a new instance of the user struct, which has the field name email. We want to set the email field's value to the value of the email parameter of the build user function. Because email field and the email parameter have the same name, we only need to write email rather than email colon email. Okay, yeah, so nicer, it looks nicer. Creating instances from other instances with struct update syntax. It's often useful to create a new instance of a struct that includes most of the values from another instance, but changes some. You can do this using struct update syntax. First, in listings 5.6, we show how to create a new user instance in user2 regularly without the update syntax. We set a new value for email, but otherwise use the same value for user1 that we created 5.2. So we create a new user here. Basically, let's delete this, and this will be immutable. Let's return this, and then we create a user2 with user1 active. It will not work. User1 active, and then we have username equals user1 username. Wait, what's wrong here? It's semicolon. Oh, maybe here. No, I have a semicolon here. Sorry, user. Yeah, I have to define what I'm creating here. So we have user, and this is a colon with a username. I wonder how this will work. If this invalidates the user1.username, we'll check this. Like if the borrow checker makes it irrelevant. Okay, so email, we do a new email, string from user2 at hello.com, and the sign in count is also user1 sign count. Okay, so now I do this. Will this work? Yeah, as I expected, because we're doing this, the username string is borrowed into the username in user2, and it's not usable. So if you want to make this work, we do a clone, and it will work. But let's keep the example as it was, because the example doesn't have the sprint. Okay, so now I have the user2, and let's see how we do this in a shorter way. Using struct update syntax, we can achieve the same effect with less code as shown in listing 5.7. The syntax ... specifies that the remaining fields not explicitly set should have the same value as the field in a given instance. So we do something like this, but first define the values that changed, and then we say take everything else from user1. Okay, and let's just make sure that it still borrows the value. If I'm trying to get username of user1, I'm getting an error that it's because it's moved and it can't do it. Okay, great. Let's just comment it out. Okay, the code in listing 5.7 also create an instance in user2 that has a different value for email, but has the same value for the username, active, and sign-in count fields from user1. The user1 must come last to specify that any remaining fields should get their values from the corresponding field in user1. But we can choose to specify values for as many fields as we want in any order, regardless of the order of the fields in the struct definition. Okay. Note that the struct update syntax uses an equal sign, like an assignment. This is because it moves the data, just as we saw in the variable data interacting with move section. In this example, we can no longer use user1 as a whole after creating user2 because the string in the username field of user1 was moved into user2. Yeah, like we checked. If we had given user2 new string values from email and username and thus only use the active and sign-in count values from user1, then user1 would still be valid after creating user2. Yeah, because the Boolean variable in use64 have the copy trait, I think. Yeah. Okay, both active and sign-in are types that implement the copy trait, so the behavior we discussed in the stack-only data copy section would apply. Okay, and I guess what it does is it does a mem copy probably into the user and then changes all the values. That's, I think, the most relevant, most easy thing to do. So yeah, we would expect that anything borrowed will be invalidated. Anything that does not implement the copy traits will be invalidated when we use this kind of notation. So we need to be careful when using this. Well, we don't need to be careful because the compiler will yell at us if we do this. So that's a good thing. Okay. Using tuple structs without named fields to create different types. Rust also supports structs that look similar to tuples, called tuple structs. Tuple structs have the added meaning the struct name provides, but don't have the names associated with their fields. Rather, they just have the type of the fields. Tuple structs are useful when you want to give the whole tuple a name and make the tuple a different type from other tuples. And when naming each field as in a regular struct would be verbose or redundant. To define a tuple struct, start with the struct keyword and the struct name followed by the types in the tuple. For example, here we define and use two tuple structs named color and point. Okay, let's define those. Struct color as i32, 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 and struct point. I think they're both i32 because they want to show us that we cannot assign one into another. I would not choose i32 for color. Okay. And then in the main, let's delete the users. I think we're done with them. Yeah. And then in the main, we do let black equals color. And then we can actually, we can input it like this. Nice. We have black. And let origin equals point, probably 0, 0, 0. Well, okay, so we have black and origin. Excellent. Note that the black and origin values are different types because they're instances of a different tuple structs. Each struct you define is its own type, even though the fields within the struct might have the same types. For example, a function that takes a parameter of type color cannot take a point as an argument, even though both types are made up of 3 i32 values. Otherwise, tuple structs instances are similar to tuples in that you can restructure them into their individual pieces, and you can use a dot notation followed by an index to access an individual value. Let's play around with this a little bit. So we can do like black 0. Yeah. And it will print cargo run. Ooh, doesn't, oh yeah, right. Yeah, it prints a 0. Okay. We can try also with writing a function, test1, that gets a color, and let's return the 932 and just c.0, and let's try to print test1 with origin. It will say that origin is not a color. Yeah, expected color, found point. Okay, let's continue. Unit-like structs without any fields. You can also define structs that don't have any fields. These are called unit-like structs because they behave similarly to unit. The unit type that we mentioned in the tuple type section. Unit-like structs can be useful when you need to implement a trait or some type but don't have any data that you want to store in that type itself. We'll discuss traits in chapter 10. Here is an example of declaring and instantiating a unit struct name always equal. Let's test it. Struct always equal. And then I can do a let here. Let subject equals always equal, and no need to do anything. Okay. To define always equal, we use the struct keyword, the name we want, and then a semicolon. No need for curly brackets or parentheses. And then we can get an instance of always equal in the subject variable in a similar way, using the name we define without any curly brackets or parentheses. Imagine that later we'll implement a behavior for this type, such as that every instance of always equal is always equal to every instance of any other type. Perhaps to have known result for testing purposes. We don't need any data to implement that behavior. You'll see in chapter 10 how to define traits and implement them on any type, including unit-like structs. Okay, I guess we'll dive deeper into this. I don't fully understand why we need this. Yeah, but we'll see. We'll see. In the user struct definition in listings phi1, we used owned string type rather than the str string slice type. This is deliberate choice because we want each instance of the struct to own all of its data for the data to be valid for as long as the entire struct is valid. Okay, that's why we're not using the ref string. Okay. It is also possible for structs to store references to data owned by someone else, but to do so requires the use of lifetimes, a Rust feature that we'll discuss in chapter 10. Lifetimes ensure that the data referenced by a struct is valid for as long as the struct is. Let's say you try to store a reference in a struct without specifying lifetime, like the following link. This will not work. So I'm defining a user, and it's with strings, and then if we do this, let's just copy paste this and get the error. Yeah, so I'm getting errors here, and the same missing lifetime specifier. Okay. In chapter 10, we'll discuss how to fix these errors so you can store reference structs, but for now we'll fix errors like these using own types like string instead of references like ref string. Okay, let's move on. An example using structs. Okay, to understand when we might want to use structs, let's write a program that calculates the area of a rectangle. We'll start by using a single variables and then refactor the program until we're using structs instead. Let's make a new binary project with cargo called rectangles. Never mind. That will take the width and height of rectangles specified in pixels and calculate the area of the rectangle. Listing 5.8 shows a short program with one way of doing exactly that in our project's main. Okay, so let's make it. fast. We have main. We have let width equals 30. Let height equals 50. And then we have print line area is, and then let's define function area that gets a width of i32, a height of i32, and returns a u32. We're doing only u32s, okay. Let's do u32s, and returns width times height. Great, and here we do area of width and height. Colon, let's run this, let's get our 1500. Okay, excellent. The code succeeded in figuring out the area of the rectangle by calling area function with each dimension, but we can do more to make this code clear and readable. Let's issue with this code an evident signature of area. The area function is supposed to calculate area of one rectangle, but the function we wrote has two parameters, and it's not clear anywhere in our program that the parameters are related. It would be more readable and more manageable to group with the width and height together. We've already discussed one way we might do that with a tuple, so let's do it with a struct. Okay, they're refactoring with a tuple, so let's do a tuple thing, this and this, and then we put rect here, and then this becomes a tuple. It's R type of i32, sorry, u32, u32, and then we return r0 times r1. Yep, let's run this. Let's get the same result. Everything's looking good. Okay. In one way, this program is better. Tuples let us add a bit of structure, and we're now passing just one argument. But in another way, the version is less clear. Tuples don't name their elements, so we have to index into the parts of the tuple, making our calculation less obvious. Mixing up width and height won't matter for the area calculation, but if we want to draw the rectangle on screen, it would matter. We would have to keep in mind that width is the tuple index 0 and height is the tuple index 1. This would be even harder for someone else to figure out and keep in mind if they were to use our code, because we haven't conveyed the meaning of our data in our code. It's now easier to introduce errors. So now we refactor it into structs. Let's just do it without looking at the result. I think we'll do something like this, and then we have width, which is a u32, and height, which is also a u32, and now we create a rect here. Let's see if I can. No, I have to create this. We have width, width 30 and height 50. Create a rect, and here I require a type rect. Let's do this even, and then rect width, height, and a reference here. Looks okay. Let's run it. It's still 1500. I think we can also do it with a tuple. Can do it like yeah, but it's not named, so not good to do it with a tuple, the struct. But yeah, now it works. Let's see that it's the same here. So we have the definition here, width and height. We generate it like this, print it, and then you have this, and they also use the reference. Nice. Here we've defined a struct named rectangle inside any curly brackets. We define the fields as width and height, both which have type u32. Then in main, we created a particular instance of rectangle that has the width 30 and height of 50. our area function is now defined with one parameter, which we've named rectangle, whose type is an immutable borrow of a struct rectangle instance, as mentioned in chapter 4. We want to borrow the struct rather than take ownership of it. This way main retains the ownership. Yeah, that means we can use and print rect after this. Like if we want to do this, we can do like height is rect height. So this works now. If we run it, this should work. It should write 50. But if I remove this and do this, this will be an error. Yeah, because then the function borrows the value and does not return any ownership. So the ownership dies here and rect is no longer valid. Let's get this back. Okay. Okay, and now the signature of the function says exactly what we mean, that it take a rect and return the width times the height. And it gives descriptive names to the values rather than using the tuple index of 0 and 1. This is a win for clarity. As adding useful functionality with derived traits. Okay. It'd be useful to be able to print an instance of rectangle while we're debugging our program and see the values of all its fields. Listing 511 tries using the print line macro as we have used in previous chapters. So if I'm trying to print the rect area of, let's see, something like this, of rect is, so we're trying to print rect, and it says rect doesn't implement std format display. Okay. If we compile the code, we get this error. The printline macro can do many kinds of formatting, and by default, the curly brackets will tell printline to use formatting known as display output instead of directly end-user consumption. The primitive types we've seen so far implement display by default because they're only way you'd want to show one or any other primitive type to a user. But with structs, the way printline should format their output is less clear because there are more display possibilities. Do you want commas or not? Do you want to print the curly brackets? Should all the fields be shown? Due to this ambiguity, Rust doesn't try to guess what we want, and structs don't have a provided implementation of display to use with printline and the curly bracket placeholder. If we continue reading the errors, we'll find helpful notes. The trait is not implemented. In format strings, you may be able to use the colon question mark or colon hashtag question mark for pretty print instead. Let's try it. The pretty print macro will, the print line macro will, call will now look like this. So if we do this, do this, okay. But now I can't use it inside the curly brackets here. I need to use it outside here. So if I'm using this, sorry. Rust doesn't implement debug. Okay, yeah. If you put this, say Rust does not implement debug. The debug trait enables us to print our struct in a way that is useful for developers so we can see the value we're debugging our code. Compile the code with this change and we get this. And again, the error that we see is here is add derive debug to rect or manually implement debug for rect. Okay, so we need to add this. React does include functionality to print out debugging information, but we have to explicitly opt in to make that functionality available for a struct. To do that, we add the outer attribute hashtag derive debug just before the struct definition. Okay, so this is some sort of decorator, or how do you call it? Attribute. They call it an attribute. I think I'll learn about this in later chapters, but now it looks like it works. Let's see how it prints the information. Okay, so it prints this with curly brackets and field names and everything. Okay, and I think it's opt-in because it does create some sort of overhead with the file, with the exe file, that has to have a function that can print the curly brackets and store the names of the variables. And I guess in release mode we will not want to have the variable names stored in the executable because they're irrelevant when not debugging. Okay, this is the example. Now when we run the program, we won't get any errors and we'll see the following output. Yeah, we can see that here. Nice. It's not the previous output, but it shows the values of all the fields for this instance, which would definitely help during debugging. When we have larger structs, it is useful to have output that's a bit easier to read. In those cases, we can use the hashtag question mark. See, if we do this, what we get? We get a formatted string with line breaks. I like this better. Okay, and yeah, we get this line breaks. Another way to print out a value using the debug format is to use the dbg macro, which takes ownership of an expression, as opposed to print line, which takes a reference. Prints the file and line number of that debug macro occurs in your code along with the resultant value of that expression and returns ownership of the value. Note, calling a debug macro points to the standard error console, okay, as opposed to print line, which is in standard output. We'll talk more about standard error and standard output with writing error messages. Okay, so basically, for those who don't know, there are several pipes that you have in your console. One of the usual, when you print, it's standard output, but there's also a special pipe which has different caching and buffering rules, which is called standard error, and you can print out to that pipe as well. So here an example when we're interested in the value that gets assigned to the width field, as well as the value of the whole struct in rect, and we can use the debug macro of rect. Let's just see that it prints out. Yeah, so we have the file number, the file name, line number, and the entire rect. Great. Okay. We can put debug around the expression 30 times scale. Yeah, let's look at that. We have scale 2. And we can put this. And because debug returns ownership of the expression value, the width field will get the same value as if we didn't have the debug called there. Okay, so because debug returns the reference, that means I can put it inside expressions and it will not make the object or variable invalid. Yeah, because if I'm doing something like this will be an error. Yeah, and if I'm doing this, it will not be an error, probably. Or still, no. Not an error, but if I'm doing this is not an error as well. Or, it's mutable, so I need to do a let here. I'm doing this is not an error as well. This is no longer valid, it gets eaten up by debug, then debug returns another rect, and then I put it into here, and then I can still use it. Great. Okay, we have this. Let's read. We can see that the first bit of output came from source main, line 10, where we blah, 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 blah. We saw that. In addition to the debug trait, Rust has provided a number of traits for us to use with the derive attribute that can add useful behavior to our costume types. Those traits and their behaviors are listed in Appendix C. We'll cover how to implement these traits with costume behavior, as well as how to create your own traits in Chapter 10. There are also many attributes other than derive. For more information, see the attributes section of the Rust reference. Our area function is very specific. It only computes the area of rectangles. It would be helpful to tie this behavior more closely with our rectangle structs, because it won't work with any other type. Let's look at how we can continue to refactor the code by turning the area function into an area method. Okay, let's move on. I think we'll do this and then finish the video. Methods are similar to functions. We declare them with the fn keyword and the name. They can have parameters and return value, and they contain some code that run when the method is called from somewhere else. Unlike function, methods are defined within the context of a struct or an enum or a trait object, which we cover in chapter 6 and chapter 17. And their first parameter is always self, which represents the instance of the struct the method is being called on. Okay, so we have this code from, just copy it, make sure we didn't do any changes. So we have the debug, we have the rectangle, and this is the method. Okay, so we have impl rectangle, and then we have a function inside that gets a reference to self, returns a U32, and then we can run this like this. So I guess this is what we're going to read here. So to define a function within the context of a rectangle, we start an implementation block for the rectangle. Everything within this block will be associated with the rectangle type. Then we move the area function within the implementation curly bracket and change the first, and in this case only, parameter to be self, in the signature and everywhere within the body. In main, we called the area function and passed rect1 as an argument. We can instead use a method syntax to call the area method out of the rectangle instance. The method syntax goes after an instance and add a dot followed by the method name, parentheses, and any other arguments. Any arguments, but I think it's any other arguments. Yeah, if we have additional arguments here, I think they go here. In this signature area, we use self instead of rectangle ref. Rectangle, the self is actually short for self with an implementation block. The type self is an alias for the type that the implementation block is for. Methods must be a parameter named self of type self for their first parameter. So Rust lets you abbreviate this with only the name self in the first parameter spot. Not that this still an instance, just as we did in rectangle ref rectangle. Methods can take ownership of self, borrow self immutably as we've done before, or borrow self mutably just as they can any other parameter. So yeah, this is just a short to write. I don't have to specify the type here because we're inside an implementation block of a rectangle. So Rust assumes that the first parameter is a self. It knows the type. Makes sense. We chose self here for the same reason we used ref rectangle. In this function version, we don't want to take ownership and we just want to read the data in the struct, not write to it. If we wanted to change the instance that we've called, the method of this part of what the method does, we'd use mutable self as the first parameter. Having a method that takes ownership of the instance by using just self as the first parameter is rare. This technique is usually used when the method transforms self into something else and you want to prevent the caller from using the original instance after the transformation. That's interesting. So we could use this, but that means that when you use this area method, it makes the rectangle that you passed onto it invalid. So this is like a way to invalidate previous data. Maybe we'll need this sometimes in the future. The main reason for using method instead of function is additional to providing method syntax and not having to repeat the type of self in every method signature is for organization. We've put all the things we can do with an instance of a type in one implementation block rather than making future users of our code search for capabilities in rectangle in previous places in the library we provide. So this is like good for organization basically. I don't think there's a big difference from just declaring a function to a member from doing this method, but this is more pretty, it's more understandable. I know what to look. I can look for implementation rectangle if you want to see which methods are implemented. Yeah, this is better. Not that we can choose to give a method the same name as one of the structs fields. For example, we can define a method on rectangle that is also named width. Can we do this? Function width. Let's have function width that gets the self, returns Boolean, and self width greater than 0. Okay, this returns true if the rectangle has width. And we can run it like this and with an if. Let's do this here. Great. Here we're choosing to make the width method return true if the value of the instance width field is greater than 0 and false if the value is 0. We can use the field within the method for the same name for any purpose in main. When we follow rect width with the parentheses, Rust knows we mean the method width and not the parameter. When we don't use parentheses, Rust knows we mean the field width. Often, but not always, when we give a method the same name as a field, we want it only return the value of the field and do not do anything else. Methods like this are called getters, and Rust does not implement them automatically for struct fields as some other languages do. This is very good. Getters and setters. I don't like getters and setters as defaults. Getters are useful because you can make the field private with the method public and thus enable read-only access to that field as part of the type's public API. We will discuss what public and private are and how to designate a field or a method as a public or private in Chapter 7. I don't know how I feel about public and private. Sometimes it's useful, sometimes it's just cluttering, and sometimes it hides things that should not be hidden just because someone made a decision that this should be private and did not understand the full scope of the needs. So we'll see. In C and C++, two different operations are used for calling methods. You use dot if you're calling a method on an object directly, and an arrow if you're calling a method on a pointer to the object, and needs to be dereference the pointer first. In other words, if object is a pointer, then you use an arrow, and you can dereference this pointer and use a dot. Rust doesn't have an equivalent to the arrow operator. Instead, Rust has a feature called automatic referencing and dereferencing. Calling methods is one of the few places Rust has that behavior. Here's how it works when you call a method with object something. Rust automatically adds in ref mutable, or dereference. I think it's a dereference. The object matches the signature of the method. In other words, the following are the same. Okay, yeah. So I can use this object, or can you take a reference to the object and use this. The first one looks much cleaner. This automatic referencing behavior works because methods have a clear receiver, the type of self. Given the receiver and name of the method, Rust can figure out definitely whether the method is reading a self-mutating self or consuming. The fact that Rust makes boring implicit for methods receivers is a big part of making ownership ergonomic in practice. Okay, that makes sense. It's easier. I don't have to think about dot or arrow, but I think now in all the dynamic IDEs, it's not a problem anyway. Method with more parameter. Okay, so let's practice using methods by implementing a second method on the rectangle struct. This time we want an instance of rectangle to take another instance of rectangle and return true if the second rectangle can fit completely within self, the first rectangle. Otherwise, it should return false. That is, once we have defined the canHold method, we want to be able to write the program shown in listing 5.14. So let's just copy this program first, and it will say that we don't have canHold. So let's write a function canHold that gets self and another rectangle. It will be a reference to a rectangle. We don't have to invalidate it. Returns a Boolean number, and I think that's it. Oh, sorry, rectangle. Yeah, so now we just have to do the calculation. The expected output would look like the following, because both dimensions of rect2 are smaller and the dimensions of rect1, but rect3 is wider than rect2. So we expect to get this. So now we have to just implement this. So the function is very easy. We just return if self width is bigger than the R2 width and self height is bigger than the R2 height. And that's it. Let's run the function and we get true and then false. Yeah, we understood this. I think here they're explaining that I can put the second parameter here, and when I call it like this, omitting self, and they explain the algorithm of comparing width and height. Not going to read this. When we run this code, the main function of listing54 will get our desired output. Methods can take multiple parameters that we add to the signature after the self parameter, and those parameters work just like parameters in functions. Makes sense. Okay, associated functions. All functions defined with an implemented block are called associated functions because they're associated with a type named after implementation. We can define associated function that doesn't have self as their first parameter and thus are not methods because they don't need an instance of a type to work with. We've already used one function like this, the string from function that defined on the string type. Associated functions that aren't methods are often used for constructors that will return a new instance of that struct. These are often called new, but new isn't a special name and isn't built into the language. So there is no new in Rust. For example, we could choose to provide an associated function named square that would have one dimension parameter and use that as both width and height, thus making it easier to create a square rectangle rather than having to specify the same value twice. So let's write this. A function square that gets a size of U32 and returns self. Okay, this is important. And then it's self with size and height is also size. Makes sense. So the new thing here is that the self is a rectangle. It automatically becomes a rectangle, so we can actually have here, if I do this, I can probably do, before peeking, I can do square and just run it with 70. And this will return a rectangle with size 70 by 70. That is the example. The self keyword in return type and in body of the function are aliases for the type that appears after the implementation keyword, which is in case rectangle. Yeah, I'm not sure this is good. Yes, it's good, I think, for like copy pasting things, but copy pasting is not very good. So let's see. Actually, I'm using rectangle here. Will this be okay? Run it. Yeah, it looks okay. So I don't know if I want to use the self here. We'll see. We'll see how it goes. Multiple implementation blocks. Each struct is allowed to have multiple implementation blocks. For example, listing 515 is equivalent to the code shown in 516. Okay, so I can split it. There is no reason to separate method into multiple blocks, but it is valid syntax. Okay, we'll see a case in which multiple implementation blocks are useful in chapter 10, where we discuss generic types and traits. So if you have generics in the language, I think self will work great here because you don't have to specify the generic decoration that you usually have with generic. Okay, summary. Structs let you create custom types that are meaningful for your domain. By using structs, you can keep associated pieces of data connected to each other and name each piece to make your code clear. In implementation blocks, you can define functions that are associated with your type, and methods are a kind of associated function that lets you specify the behavior and instances of your structs have. But structs aren't the only way you can create custom types. Let's turn to Rust's enum feature to add another tool to your toolbox. Enums we'll do next time. I think the video is running long. So we finished the entire chapter. That's good. Next time we'll do chapter 6. Yeah. So see you then. Bye.